So yeah, I did this while a PhD student at Oxford. I was in the computational stats group there. So Mike just kind of caught me off guard one day at the Turing Institute and told me, hey, Thibaut, you did this package in Julia. Do you want to talk about it to a meetup? I was like, yeah, okay, sure. and so I hope, I didn't really know how to prepare for this. So what I'm going to do is I'll tell you why I wrote this package, maybe like a little bit about the theory of something called a bouncy particle sampler. I won't dig too much into details. I think it kind of depends on how interested you are in that kind of stuff. I'm guessing from just a curiosity perspective, hopefully it'll be enough. And then I'll talk a little bit about my experience with Julia that I'm still using quite a lot, and what I like and what I don't like so much. Yeah. So. Right, so what I'll talk about is a little bit about Bayesian inference, how it relates to something called sampling. Then I'll talk about some classical methods, MCMC and HMC. I won't dig too much into details, but these are like the bread and butter of anyone doing Bayesian inference. And then the bouncy particle sampler, or BPS, is a pretty new type of algorithms that is part of something called rejection-free algorithms. So I'll talk a little bit about that. And then the local BPS, which is just a version of it. And I'll finally talk a little bit about Julia, just maybe a little bit. Just to know what are people's interests here. So I do recognize you. I know that you're in bioinformatics, right? Can I just get a quick raise of hands? Who's in like CS or a CS background or applied math? Right, and physics and others. Where are the others? Oh, well, bioinformatics, chemistry, other non-tech. No? Okay.
I used to think chemistry is non-tech.
Sorry, no, non-tech. I meant like, well, I guess you can do computational chemistry as well. Or maybe another way to put this question, how many of you know Bayesian inference? Ah, that's going to be fun. All right. You all know it really well, or like just you're aware of what it is? I'm curious, because otherwise this will be boring. I can skip to the final slides already. No? Okay. Well, I won't go too slowly then on the intro stuff, which is good because I don't have too many slides on the intro. I'm guessing, I don't really know how confident you were on raising your hands. I might question you during the talk. But I'm guessing most of you know what a posterior distribution is, and probably you have heard some of MCMC. I'm kind of guessing you may have some idea of what HMC is, but maybe not so good. And I'm guessing you have never heard of the bouncy particle sampler. Is that fair to say? Yeah? Okay, cool. Good. So just for those who haven't raised their hands, Bayesian inference is about something called probabilistic modeling. So a standard example, which I'll use for the first few slides, is if you're considering a linear regression model in 2D, so really like your vanilla 001 stats model, where you get your output yi as a linear combination of an observation xi, so alpha plus beta xi, plus some noise, and you don't know what the noise is, obviously, but you suggest a noise model as a Gaussian distribution centered around 0 and with some fixed variance. Okay, so that's like super standard stats model. And then the question is, you've observed some data, which I will call D, and it's unfortunate that the screen thing is kind of slicing my equation in two, but anyway, you've got effectively the likelihood, and we'll work with this in the remaining of the talk, you've got a likelihood of the observed data given two parameters, alpha and beta, and either you recognize this, and if you don't, that's okay, but this part is a Gaussian distribution, right? So you're basically saying, and the specific form doesn't really matter, what you're just saying is, I've got my model, which is the alpha plus beta x, and then I've got a likelihood around it, which tells me, well, if I plug in one alpha, say 0.5, and one beta, say 2.7, how likely is my data going to be, given that I'm assuming this model is what generated the data? And so if you know about frequencies versus Bayesian stuff, you know that frequencies typically do maximum likelihood estimation, so they will try to find the alpha and the beta such that you maximize the likelihood. So you're basically saying, my model is the truth, now give me the parameters for my model such that it matches the data as well as possible. And this is an optimization problem, right? You massage the previous equation a little bit, use a log somewhere, and you'll get like the perfect alpha and beta to match the data. So that's called the OLS, ordinary least squares equation. It's very easy to get, and there is even an analytical form for the parameters. Great. And so, by the way, I'll refer to this. If you're fairly confident with Bayesian inference, you will know that Bayesian inference is basically integration wherever frequentists are doing optimization. Okay, so I'll bring that up again, but it's a key element to understanding what's the difficulty with Bayesian inference and why are people struggling with it still today. Okay, so now, and I'm guessing again, this is probably doesn't come as a surprise, a prior encodes what parameters are more plausible based on what you know. So it might be your experience, it might be previous experiments, or it might just be your gut feeling. But let's say in my linear model, I might expect the slope not to be 1 million and the intercept not to be minus 500,000, right? So you're kind of saying, already intuitively, you're saying there is a range of likely parameters, and away from that, I think, you know, it's unlikely. I'm going to penalize models that are too far away from what I expect my model to be. So you can encode that using a prior, and you can see that I didn't use ticks to do this because I was a bit lazy. But effectively, you have a distribution of, I mean, the intuition is all we need here. You have a distribution around parameters away from what you would call likely. You just say it's unlikely. And what that means, or how that translates into the code is, well, what's not likely is penalized. So effectively, you'll try to not obtain candidates there. You'll try to focus your optimization in the area where things are more likely. And so, of course, you know what comes next. If you combine the likelihood with the prior, you get a posterior distribution. So Bayes' rule gives you that the distribution over the parameters, given the data, is proportional to the likelihood of the data given the parameters multiplied by the prior. I'm kind of going quickly here, but I'm guessing you all have seen this before, or most of you. So what does that actually tell you? So that's just, it's not even a theorem. It's just massaging equations, right? So the only thing it tells you is you can relate the likelihood and the prior, and what it gives you is a distribution over parameters. So P of theta given D, or the posterior, is a distribution over parameters given the data and the prior, and that tells you, that's kind of a way to tell you, well, these parameters, given the data and your prior, are more likely than others. And obviously, the next step is, well, I care more about likely parameters than not, right? The normalization constant, so here I use a proportional symbol. The normalization constant is typically very hard to get and typically not needed as well. I might shove that under the rug for now, but if there are questions, I'm happy to take them later. And so if you don't know Bayesian inference, you might think, well, okay, so he's given me another expression, posterior distribution, fine. He wants to penalize stuff that are unlikely based on this prior. So now the only thing we need is find the best parameters for that posterior. So instead of doing maximum likelihood estimation, why not do maximum posterior distribution or maximum a posteriori estimation? Okay, so that's called MAP, which is basically exactly the same as MLE, just with a penalty that accounts for whatever prior you picked. But the posterior, and this is very important, the posterior encodes far more than just what your parameter should be. It also encodes a notion of uncertainty, or it encodes how much your, if you think that your data is a linear model, right, is beta at 2.5 so the slope at 2.5, maybe that's the best parameter, but if I put it at 2.4, is it really significantly different? How much spread is there around the optimal parameter? And that's definitely something we would be interested in. So I've got this nice representation here, also not ticks. So let's say that your optimal beta is here, and you can see that it's the high point of this probability distribution function, so the posterior, right? But you should get the idea that there is quite a lot of a spread here. Of course, I didn't give you a scale, so this is actually a dubious statement, but there's quite a lot of spread, at least intuitively, right? And if you give your model to a customer and you want to say, well, I think beta is 2.5, you should also tell them it's 2.5, but the data is quite messy, and actually, you know, there is a lot of noise around it, and beta 2.3 would work just as well, right? Which is an important information, because if you're trying to do predictive modeling, this should come into the game in order to give confidence about your model. So if you're trying to predict out of sample, if you have a data point that's completely outside of your training data, you should be able to model the uncertainty around whatever prediction your model gives. And this, integrating the posterior, this does give you that. So that's fantastic. That's what we want. That's the ideal world scenario. So we want to characterize posteriors. The problem is typically you don't really have access to the full posterior. You don't know what it is. Maybe some of you, if you've done stats, classical stats, you know that if you have things called conjugate priors, do people know this? Yeah. If you have conjugate priors, great, things just come nicely and you actually know what form of posterior you're going to get. In the real world, this never happens. You never have conjugate priors, and people who tell you you should use conjugate priors are actually lying, and it's effectively forcing you to use specific priors, and therefore you're not really doing what you want to do, right? Okay, so we want to be able to characterize the whole of p theta, the posterior, and we can usually compute this posterior pointwise up to a normalization constant, because you just plug in the likelihood, which you have, it's just your model, and you have your prior, which you've picked, so that's also something you can compute, right? You don't have this normalization constant, but actually we don't really care so much about it. And we want to be able to characterize a distribution. So to characterize a distribution, there are several things you can look at, and usually you look at things called moments, or expected values of specific functions that you care about. So things like mean, variance, skew, all of this can be computed using one type of function called expected values. All right, so these expected values are, and this is where the integrals come in. These expected values always have the same form, and it's the expected value with respect to my target distribution, so this posterior distribution, of some function phi. It doesn't matter what for now. If you're thinking about the mean, it's just x. Or if you're thinking about the variance, it's going to be x squared somewhere. And it's given by an integral of the function I care about, weighted by this posterior distribution. But now we went from, early on I told you about MLE and MAP, and this was optimization problem. It turns out optimization is fairly easy in quite a lot of scenarios. This is an integration problem, and as soon as you have dimensionality of that thing, that theta here, the parameter of interest, as soon as you have dimensionality above, let's say, 3 or 4, you can't use your Simpson method or Riemann integral or whatever deterministic integration method you may want to use. So this brings me to the core of the game, sampling. You may know of quadrature, right? If you want to compute integrals approximately, pretty much all the time it's going to look like this, a weighted sum of the function evaluated at some points. And the points, you pick them appropriately, and depending on which rule you look at, well, it's going to be Gauss-Legendre, Gauss-Hermite, you know, like there's a bunch of names, usually French guys or German people or whatever. But they will always try to integrate specific functions like polynomials or up to a certain level of confidence. And all of this works quite well, but as soon as your dimensionality goes up, all of those break down. So they tend to have some convergence rate, but that convergence rate is moderated by dimension. And so at some point, that convergence rate becomes really, really slow because your dimension is just too high, okay? So that's why people look at Monte Carlo integration, which is exactly the same thing, except that now my xi are randomly drawn from the target distribution P. And the nice thing there is dimension don't matter anymore. The same convergence rate, 1 over square root of n, applies, and that's it, right? So the good is properties don't depend on dimension. The bad is obviously how do you generate points from P? I kind of led you here, right? I told you, well, it would be nice if, but I just told you we could compute the target distribution, the posterior. We could compute it point-wise, but not generate points from it. So now the whole thing boils down to sampling problem. For an arbitrary distribution pi, and it can be a posterior, but this problem is more general, right? It's for any distribution over random variables. Can you generate samples from pi? And this is just basically Bayesian inference is that. Computational Bayesian inference is that. If you can, then you can approximately compute the moments using the Monte Carlo method I just mentioned before. So let's see what 2 standard approaches to generate points from an arbitrary distributions are, in particular MCMC methods and HMC. And then that will bring me finally to what the package is about. So the general idea of Markov chain Monte Carlo methods and Hamiltonian Monte Carlo methods, so MCMC and HMC, is often kind of around a similar scheme. So you use a mechanism to explore space, so to explore the valid parameters that you can have for your model. And you have another mechanism that tells you whether a point on that space is good or not, right? Usually a coin flipping kind of experiment. So you want to, let's say the parameters for my linear regression, right? Potentially my alpha and my beta can be anything from -infinity to infinity. So together, that's the whole of R2, right? It's the plane. And here you would want a mechanism to explore R2, so something that generates points on R2. And you would want something that tells you whether a generated point should be kept or not. Okay, so that's called an accept-reject mechanism. And usually, of course, whether you accept or reject is based on density. So if your probability distribution function has high values in that area, then you have a higher likelihood of accepting. And if you're in an area which is very unlikely, well, you shouldn't accept, right? So MCMC is just one specific way of doing this. You generate points based on a proposal. So that's a distribution that is easy to sample from. And then you accept or reject based on the ratio of the target to the proposal at that specific point you generated. So let's see here, I've got a target which is this weird bimodal distribution. And as a proposal, I use a pretty wide Gaussian. That's easy to sample from. I can sample from a Gaussian, no problem, right? The problem is that proposal, well, here it will generate far more points than it needs. Here it will generate too few, right? So you just get all these points, and then you need to accept a little bit more when you're in this area, and accept a little bit less when you're in those areas, right? That's the whole principle. But you get this idea, and I think here the key message is not really how the method works, but rather that we're generating points and rejecting points. So if your proposal is crap, guess what? You reject a ton of points, and you sample in the right areas very seldom, right? So of course here that would be a pretty good proposal, because it covers everywhere where there is mass in the distribution, right? So you would generate points in effectively the right place. You just need to adjust a little bit to make sure that you're weighing some areas a bit more and some less. But roughly speaking, it's going to do a good job. Now, to maybe give you a bit of intuition, if we have a target distribution which is like this, right? That would be really horrible, by the way. That's very difficult to deal with. And you put a proposal that's here, that's not going to work too well, okay? You're going to generate lots of points here. Then you're going to try to reduce their weight a lot. You're going to generate very few points here and increase their weight a ton. So that's going to make, I'm not going to go too much into details, but the variance of your estimator is going to explode and things are going to go horribly wrong, okay? Good. So Hamiltonian Monte Carlo method, which is very popular, pretty much the method of reference at the moment. What it does is, instead of generating points from a proposal, it follows a trajectory in space, which is modulated by your density. So in areas of high density, it will move in a specific way, and in areas of low density, it will make large movements. So basically, from the current point, the way it works is from the current point, maybe I'll show you this first, and then I'll go back to the previous slide. You start with a current point xn and some momentum variable, and then you follow a trajectory that corresponds to the solution of something called a Hamiltonian. If you've done some physics, you know what this is. This Hamiltonian encapsulates both the density, so the target distribution on the one hand, as well as a parameter that promotes exploration. So you want two things, right? You want to be able to know where the distribution is, so that's the first part. And you also want to explore the space sufficiently so that you don't miss out on some regions, okay? So that's what the Hamiltonian covers both of these terms. And so you compute these trajectories from the current point, you compute the trajectory to a new point, and then you accept or reject that new point based on, and doesn't matter so much, but based on the evolution of the Hamiltonian. So the whole point here, and I mean, I'm more than happy to talk far more about MCMC and HMC, but I'm afraid like I might kill everyone. The key point is this accept-reject mechanism. So you generate a lot of points, and potentially you kill a lot of those, right? So optimally, I think for HMC, the ratio is like 63% acceptance rate. And that's if you've done everything perfectly, which never happens, right? So usually it's far less, which means that if you want to generate a ton of points, then you have to generate a ton of points, usually plus 50% of nothing that you just go throw to the bin. Okay, so the Bouncy particle sampler is here to help, or at least we try. So the idea is it's a rejection-free mechanism. There is some elements that are similar to what was being done before in that it follows a trajectory. But now instead of being a curved trajectory, it's just a piecewise linear trajectory through space. And for what it does is it has a point here, xn, and for every point, there are two additional things, a velocity and a time of travel. So the velocity will tell you which direction you should go next, plus how quickly. And the time of travel, well, how long should this segment be, right? So that's a mechanism to explore space, fine. Now, how do we guarantee that this generates an appropriate trajectory for Monte Carlo, et cetera, et cetera? So the nice thing is no rejection. Bounce computations are simple. I won't go into the details, but basically it's you look at where you are corresponding to the target distribution. If you're in areas of very low density, very low mass, so very unlikely events, you're going to bounce back pretty hard. If you're in areas of high density, you're not going to bounce too much, right? And you can deal directly with something called domain constraints. So for example, let's say you know that your parameters are positive, right? Well, then you can bounce off the boundaries of those constraints pretty easily using exactly the same mechanism. So that's very nice, and that's something that you can't do so easily with MCMC or in fact HMC unless the boundaries are very simple. So if the boundaries are a bit complicated, basically you're dead with HMC. So of course, what's not so nice is the length of the trajectory. So this tau symbol I had before, I can show you the slide with the process before. The length of the trajectory is dictated by a random process. So maybe I can give you an idea here. Let's say you're at this point here, and you have this velocity. You know where you have to go next. But for how long, that tau is drawn from what is called an inhomogeneous Poisson process. And I will definitely not go into that. But it's a process. You may know Poisson process, fine, like counting processes, etc. But the details of how you sample from that process are not so nice. It's quite hard, in fact. So the whole thing, it basically means for HMC, we have this accept-reject scheme, etc. Everything is pretty simple, but we throw away quite a lot of the computations. Here, everything is nice and simple, but we have to compute or sample from this complicated process, which, guess what, may require a rejection mechanism. So you never win completely. But it... Pardon? Yes. So the good thing is it's okay for simple target distributions. So let's say, well, of course, the Gaussian, but maybe others as well. Like linear models typically would work well, generalized linear models. But the problem is, for those simple models, well, HMC will just still do better, right? So more research is needed to really prove that it's actually useful and in what circumstances it's really useful. So there are circumstances where the constraint, the domain is constrained by some weird constraints, definitely very useful. And definitely probably you can't use anything else than that. But otherwise, let's say if you have an arbitrary domain and you're comparing HMC with BPS, it's not going to be very clear which wins. Actually, often both require a significant computational effort and both will be not so great at generating points. Okay. But there is something called the local BPS, which I quite like. And so here I need to talk a little bit about something else. How many of you have heard what a graphical model is? Half the room, okay. So maybe I'll just give you the intuition first. A graphical model encodes conditional dependent structure. Let's maybe just, for the intuition, if you have independent variables, independent random variables, right? Then you should know from stats that the joint probability is the product of probabilities, okay? The slightly more complex generalization of that is called conditional dependent structures, where it does still factorize, but in a non-trivial way. Instead of being every random variable has its own little term, it now becomes, let's say, pairs of variables have their own little term. So that's what I'm representing here. Let's say you have 3 random variables, and this would be a conditional dependent structure, where with theta1 here being one of the random variable, and then the 2 others depend on theta1. So you would represent this like this. okay? Meaning that both theta 2 and theta 3 are related to theta 1, but conditionally they are independent, okay? This happens a lot. In most models, so like hidden Markov models, or neural networks, et cetera, most models have some kind of structure, underlying structure like this, by construction. So the nice thing here is, and maybe just again to give some intuition, the nice thing here is that's three-dimensional distribution, whereas these are one- and two-dimensional distribution. For hidden Markov models, well, it doesn't matter which kind of models, but generally speaking, on the left you will have something that's very high-dimensional, maybe like 50 random variables or maybe even more. And on the right, you just have a product of many terms which have dimension 2, 3, 1, right? So at least from just getting a feeling for this, we'd want to be able to leverage this, right? We'd want to be able to sample maybe just from these small things, or maybe with a little bit more, so that we don't have to sample from the big space, which seems like a huge waste of time, okay? Turns out this is very difficult to do. And methods like HMC can't do it, and in fact, no methods can really do it at the moment. Though the local BPS can, but with a few caveats. So, maybe just again to give an idea of why the local BPS can do it, you can generate trajectories for every, these piecewise linear trajectories. You can generate them for every single variables individually, and then have something called a scheduling for which variable should be updated next. And overall, especially if your graph is, if the conditional dependent structure is called sparse, meaning that most variables are connected to one or two other variables, and overall, if you drew the full graph, it will look like a tree kind of thing, right? If you have that, then the local BPS does a pretty good job. Okay, so reduces the problem to a set of small dimensional problems, and I may just say it deals nicely with conditional independent structure, reduces the overall dimensionality of every individual problem by really a lot, and it works quite well for very sparse graphs. So I just want to make sure this is clear. So let's say so a hidden Markov model which looks like this. I don't know if you've seen this before. So that's the standard example for a time series, for example, where you have an underlying state of interest and an observation that depends on the state, and subsequent states are linked to the previous one, right? So in here, that's very sparse connection structure, right? This one only talks to this one only talks to that one. There are no crazy links everywhere. If you added links like this, that would be another model, I don't know what, but that's not sparse anymore, okay? And effectively what the local BPS does is it looks at every single node of that graph and it updates connected nodes. But so if it's connected to a lot of nodes, it will update lots of nodes, right? That's where there is a bit of a caveat. So the ugly is, well, it's fairly complex to implement it. Which node to update is a little bit annoying to work out, but it's, I mean, once it's coded, it's coded. And the other thing is, if the dependent structure, so if most variables are connected to other variables, then you're screwed, it's not gonna work. If you have a dependent structure which is very sparse, like the hidden Markov model, then you win, okay? Though it's still, I mean, this stuff is really fairly new, so if you're hoping to use this for your application, I think, I mean, I'll gladly talk to you, but it's probably gonna require some work. Okay, right, so now I can talk about some Julia. I mean, unless there are some questions about the math part. Yeah.
Was the comment about the graphical structure, was that particular to BPS, or I guess it would be true of any
So if you're looking for, if you're looking at continuous structure, continuous state space, so the variables of interest are continuous, right? Then no other schemes than the local BPS can deal with the graphical model structure. There are approximate schemes that can deal kind of okay with it, but no exact scheme, and this is an exact scheme. The subtlety is a bit tricky to get, but does that make sense? So if you look at, let's say, if you want to use HMC on a hidden Markov model, you're in a world of pain. Yeah, sorry.
Not sure your comment, because there are so many dimensions in this. Just wanted to question something that you just said. Only BPS can deal with functions. But if I work with Coppola 1A, the thing that you said, everything else is approximate, and yours is the only one that doesn't exactly.
It's not mine, by the way. It's, yeah.
So with buying Coppola in position, the likelihood, where the only approximation, so it's kind of, again, depending on position, the factorization into that area of Coppola's is just by construction, so there's nothing strange there. But usually you omit the way the variables that are not in your area Coppola interact apart from the machine. So suppose you want x1, x2, you can have x1, x2 conditional on lots of other things, again. But in order to be exact, you have to introduce them twice.
Hmm.
Typically people don't do that because the majority of the Coppola families is very different. So is this what you refer to by saying?
So I'm not super comfortable with copulas, so I would rather not comment too much on this. I'm happy if we talk later on the whiteboard. But as far as I'm aware, when I mean exact is if you take the full joint distribution, right? If you can have an expression that computes the expected value of arbitrary so-called test function, so this expected value of phi of x, right? If ultimately with large computational effort you get the right answer. That's what I mean by exact. So if you can only compute expected values with respect to marginals, so just with respect to to one or two variables,
I was talking about the actual function, evaluating the likelihood.
the full posterior.
No, not just evaluating the likelihood function in a particular fucking rate.
But here we're not interested in the likelihood, right?
No, I would prefer the likelihood to compute the posterior.
Yes.
All right. Whether or not I can compute it exactly or approximately, so that's what I'm after.
No, so here.
I submit some parameter vector.
Yeah.
Can I compute it exactly or approximately?
No, I'm assuming you can. Sorry, I'm sorry for the confusion. Maybe we can take this offline.
You don't compute the likelihood exactly anyway.
Right. So I'm referring to methods which can. I'm assuming that you can compute the likelihood exactly. Right. I think here when I talk about exact versus not exact, I mean about the posterior, how you deal with it, right? So for example, an inexact method would be. So if you know what variational inference is, maybe some people have heard of this, where this is, let's say, the true posterior, and variational inference will try to fit a Gaussian that kind of looks like it, right? But that's inexact because you're not targeting the right distribution. You're just trying to target a proxy distribution which looks like what you want. Does that make sense? Maybe you can. Yes. I'm happy to maybe discuss later. Are there any other questions with respect to what I presented? Oh, good. Okay, then we're in for the lighter bit. I won't go too much into details here because I'm guessing either you've done as much Julia as I have, or I'm not the right person to promote Julia. So the code is pdsampler.jl if you want to have a look, or I don't know if I should show you this, but probably not. So maybe I'll tell you, like I thought, what should I say about Julia, which is likely to be of interest to people. So I'll talk about what I like and what I don't like so much, and maybe some generic comments. So what I love as a pseudo-mathematician is that types and multiple dispatch makes a lot of sense to me. So I like to define objects as types and not as classes, and to define operations between objects. And I like the hierarchy of types. I think for me that makes a lot of sense. And I've had quite good discussions with people who are hardcore PO, oriented, object-oriented programming type. And I understand that everything that you do with a type system you can do with class. But in my opinion, personal or a small researcher, I find it's less natural. It doesn't read the same, but that's, again, personal belief. So another thing that I find quite nice is there is a real drive to try to make Julia code agnostic of whatever infrastructure you have. So you can deal with multiple processors, GPUs. I think that's really quite cool. Ultimately, I don't know how many people here do ML in production, but it seems a bit crazy that you do your prototyping in sklearn or something on your computer, and then when you want to throw it on Amazon Web Services, you have to recode everything with Scala and Spark. It seems like a little bit of a waste of time. Last thing is I find code very readable, but I guess that's acquired taste. And then, yeah, for the excited, bullet point has pointers, which is cool. R doesn't. Has the linear algebra is cool. You don't need to call C. And then it's mostly a scientific community, and people actually care about performance. Yeah, I could go on. I think I'll stop with the fanboy thing. So what I don't like is, there are ASCII symbols. Yay. What I don't like so much, and I guess it's probably a question of more of maturity than anything else. It's very decentralized, so there are very many packages, usually written by academics, that tend to be undiscoverable and are unmaintained. So that's a little bit annoying, and there are quite few attempts to build central projects. There are some, and I guess it's growing, but need more. So I'm currently actually with Mike and a few others, we're hoping to do this for machine learning. If you're interested, come and talk to us later. And then another pain point is quick incrementation is not so quick. So if you have, let's say, 3,000 lines of code, so like a basic code, and you're doing test-driven development, you're going to feel the pain of having to execute those tests. It's not the end of the world, and I think now that Juno, I guess all of you use Juno, maybe. So Juno is like an IDE for Julia, and now it's gotten really incredibly better. So this comment kind of doesn't hold anymore. So I don't really understand, these are just side comments, I don't really understand metaprogramming, but I hear it's cool. So I guess I have to learn Lisp, maybe. Yeah. Plotting is actually fine. So I used to be one of those people complaining about plots, but it turns out that now really the options are there, and even if you want instantaneous plots, you can use Gaston.jl or PGF plots, and it just works out of the box. It's a bit annoying that, again, there are at least 6 plotting packages that I know of, but yeah, whatever. And I guess this is my utopia, that R disappears into darkness where it should have stayed, and that Julia replaces it. And that's it for me. I think I hope that I've told you maybe a few things, and if you have questions, I'll be happy to take any.
I thank Thibaut, that was great. If you have questions, I'll pass the mic around so that they're recorded. Okay. We're recording this stuff. And I'll give you a Julia sticker as well, so limited edition.
Hey, I was just wondering, you mentioned when you were talking earlier about sampling that you end up having to pick a proposal distribution. I've seen them before, but I'd be interested to find out, is there like a heuristic, a way to actually choose a sensible or semi-sensible proposal distribution?
It's a great question. No, there isn't. So what people have done, and I mean, I think here there is. Unfortunately, like the hidden difficulty in Bayesian inference is often there for a reason. So the reason that there seems to be this general underlying principle of why you can't just sample easily from distribution. I think like really understanding the full uncertainty of a model is just like not trivial, right? So most of these, there are some answers that kind of make sense, but the reasons why they break down, especially in high dimension, are fairly well understood. Anyway, so that doesn't answer your question. The one way of getting, if you know that your posterior is fairly concentrated, right? So that means that like it's not crazy multimodal with modes all over the place. If you have that, you're dead. That you're not going to find any proposal that works. So if you know that it's fairly concentrated, then what you can do is have some form of variational inference that finds the right area, fits some form of Gaussian to your posterior, sample from that, and use that as a proposal. So there is like, and then there are some finer techniques. So if you look up Pareto optimal importance sampling or something like this, or Pareto smooth importance sampling, that's what they do. These are guys from Colombia and pretty good. But again, with the caveat, you kind of want your posterior to be concentrated and not crazy multimodal. And maybe just to read on the slide, philosophical note here, if you do have high dimensional problems, your posterior there is something called the curse of dimensionality, which I'm guessing most of you have heard of. And the problem is, the higher you go in dimension, the more things concentrate. So distances, I mean, I could go on this, but maybe I'll skip to the next question. But every mode, if you have multimodal distributions, every mode gets concentrated. And so eventually, with the dimension being high enough, the distance between any two modes will be very large compared to the width of any single mode. So forget about having any proposal that works with that, right? Which should be on your mind if you read anything about Bayesian deep learning. But okay, I'm not here to diss about other people's research. So yeah.
Yeah, I was just going to ask what your thoughts were about this ultra-diffuse package issue. And do you think it's just a question of grouping packages under certain banners, or is there something more organic where people could, I don't know, vote on them or something? I don't know. Yeah, it's a general question.
So I think it's a bit of a tough question. I think many people I'm fairly new to this Julia community, so I don't feel I can really speak for the masses, but I feel many people are probably like me, and that's not a good sign. In that we're academics, right? We like to write decent code. We like the idea of having reproducible open code, but usually we write code for a given paper, and then we don't come back to it, right? And so I think on the one hand, it's great, because just like R, you have a multitude of packages. Some are pretty good, some are pretty bad. On the other hand, I think having a few centralized packages that maybe draw from the multitude would be a nice way to keep smaller packages maintained. So I think the idea that we're working on is you have a ton of packages to work on specific aspects of machine learning. For example, let's say sparse linear regression, decision tree, ensemble models, et cetera. And it feels like maybe a natural way of pulling things together and make people work on the different sides is have like one central thing that can interface with all of them, and like that people would go to the central thing and just call the functionalities that are all listed there. That's maybe one thing. The other thing, and I think that's been mentioned quite a lot, is to have a place where people can discover packages. At the moment, that's quite difficult. So of course, you can go on the metadata page and scroll, but there is no like topical tree, or if you want to find all of the ML packages, good luck. I mean, if you go to the Julia ML community, there is maybe like 12 packages there, but that's only maybe half of, well, probably far less than half of what actually is available. So.